We're going to pick up with this next part of the chapter. Here, we're going to look at the actual balanced chemical reactions and see how we can use our coefficients. Remember, coefficients are the numbers that are in front of each of the compounds or elements in a reaction. We're going to use those coefficients to help us look at how quantities in our reactions are related to each other. Think back to the law of conservation of mass, which we mentioned before, which says that in an ordinary chemical reaction, matter can't be created or destroyed. No change in total mass occurs. So what that means is that the mass of the products that we end up with is going to be equal to the mass of the reactants that we started with. All right, everything that we start with has to be turned into something. All right. We can look at this sort of in reality here. We've got the reaction two silver plus one sulfur produces two silver sulfide. All right, so now if we put our silver on the balance and we weigh it, and we put our sulfur on the balance and we weigh it, when that chemical reaction is done happening, if we take the product that forms the silver sulfide and then we weigh that, we're going to see that the mass of what we end up with would be the same as if we added those two masses together. Okay, that's what our law of conservation of mass tells us. So these are some of the relationships that we can pick up from a balanced equation. We'll look at the different ways that we can relate our reactants and our products to each other with examples, but it's good to see like sort of a list of what this all means. We have our overall equation, and you're going to notice that our coefficients sort of carry through in our relationships. So two silver plus one sulfur, what that could mean is two silver atoms plus one sulfur atom would produce one formula unit of our silver sulfide. Or we could say 2 moles of silver plus 1 mole of sulfur would produce 1 mole of silver sulfide. All right. Um, when we look at the masses of these, then we can also see like 2 times the molar mass of silver, which is 247.9, or no, that's not, it's all together, it's 247.9. 2 times 107.9. Let me get that number. That's going to be our 215.8. And 1 times 32.07, which is for our sulfur. When we add those together, it's 247.9. And when we look at our product, which is the silver sulfide, the coefficient of 1 is in front of the silver sulfide in our balanced equation. 1 times the molar mass of silver sulfide is also going to be 247.9. Okay, so the law of conservation of mass. So we want to be able to look at any balanced equation. And the first thing that we want to be able to do is we want to be able to look at these coefficients that are out in front. You'll notice that when there's no coefficient out in front, we are going to assume that the number 1 is present here. And we can read these coefficients as mole values. Okay. We can also write these coefficients as equalities, and we can turn them into conversion factors. Okay. So in this particular reaction that we're looking at, just to make this extra clear, because I think setting up equalities is a good way to picture what's happening here. When we read this chemical reaction, what we can also pull out of it, we can say that 2 moles of Fe equals 3 moles of sulfur. Or we can say 2 moles of Fe equals 1 mole of Fe2S3, right? Which also means if we're continuing on with that, we could say that 3 moles of sulfur equals 2 moles of Fe, or 3 moles of sulfur equals 1 mole of Fe2S3. And these equalities are where those conversion factors come from. Because then we can take these and we can set up our conversion factors with moles of Fe on the top or moles of sulfur on the bottom, or we can switch it, moles of sulfur on the top, moles of Fe on the bottom, just depending on the question that we're being asked, right? Those different versions of our conversion factors that we look at, just like with any other kind of question or problem that we've looked at so far, we set up our conversion factors so that whatever value we're given in the problem, that value ends up as our denominator in the conversion factor. And whatever we're trying to convert into, that's what's going to be in the top of our conversion factor. Okay. But these conversion factors all come from those equalities that we can get from our balanced chemical reaction. So if we're looking at this balanced equation, 3 hydrogen plus 1 nitrogen produces 2 NH3. A mole to mole factor between hydrogen and nitrogen is going to be 3 to 1. Okay. Specifically, 3 hydrogens and 1 nitrogen. Okay. So when you look at each of these choices here, the first choice says 3 moles of nitrogen. That doesn't make sense because it doesn't match what the equation tells us. 1 mole of nitrogen, 3 moles of hydrogen, both of those match the equation. 1 mole of nitrogen and 2 moles of hydrogen, that doesn't match our equation. Okay. A mole to mole factor for NH3 and H2, NH3 and H2, say that more clearly. If you look back at the reaction, we have 3 with our H2, and we have the number 2 that goes with our NH3. So this first question, or this first choice, 1 mole of H2, that 1 mole is no good. Our second one, 2 moles of NH3, 3 moles of H2, that one looks good. 3 moles of N2, 2 moles of NH3. That's not, they didn't ask us about the N2, so that one's no good. All right, so hopefully that makes sense. You're going to look at your balanced equation, and then you're going to look back at you're going to look at that balanced equation. You're going to pull out the numbers that are associated with the specific substances that you're looking at in your question. Okay. So we're going to look at some problems. So let's write this one down. It says how many moles of Fe2O3 can form from 6 moles of oxygen? And you're going to see that the questions can vary in how they're presented. They can give you a mole value and they can ask for a mole value. They can give you a mole value and they can ask for a mass value from that. And then we would incorporate our molar mass into the calculation. Right? And they can give you a mass value and ask for a mole value. Right? We know how to connect all of these things. So any of these things are variations that we should expect to see. So we have our balanced equation, and they're asking us how many moles of the Fe2O3 can form from 6 moles of our oxygen. Okay. They're telling us that these are the two things that we want to look at and connect to each other. So we're going to focus on this relationship, the relationship of 3 moles of O2 equals 2 moles of Fe2O3. Okay. And the next thing we're going to do is we're going to write out the information that we're given. So here they're telling us that we're starting with 6 moles of O2. All right. So now when we set up our conversion factor, our moles of O2 has to go on the bottom so that these things cancel out. And our moles of Fe2O3 is going to go up top. And a 3 goes with our moles of O2, and a 2 goes with our moles of Fe2O3. Okay. 6 times 2 divided by 3. And we end up with 4 moles of Fe2O3. Okay. The second question that they're asking us here, they're just changing it up a little bit. Share the screen so that the question pops up. Same reaction, but here they're telling us a different starting amount, and they're asking us to connect it to a different part of the reaction. Okay, so they're telling us that we have 12 moles of oxygen, and we want to figure out how many moles of, excuse me, iron are required for that reaction. So in this case, the two things that we're connecting are the iron and the oxygen. So our equality is going to be 4 moles of Fe equals 3 moles of O2. We start out with our 12 moles of oxygen. Our 3 moles of oxygen are going to go on the bottom so that our oxygen can cancel out. And our 4 moles of iron are going to go up top. So we're going to have 16 moles of iron that are required to react with 12 moles of oxygen. Okay. Now in our next section, we're going to look at incorporating some of our mass values into that. Because remember, I said this is a mole to mole relationship that we've been looking at here. But we know how to work with molar masses now. And so we can also use our molar masses in these relationships to help us figure out actual mass values. All right. So if we have a balanced equation, and this is important to remember that in our balanced equations, these are mole relationships that we're looking at. All right. So if we're given a mass value of a particular substance, our first step in that process of relating it to a second substance is going to be to convert the mass value into moles. And whenever we're converting a mass of any substance into moles, we're always going to use the molar mass. The molar mass is from our periodic table, and our molar mass represents the grams of that substance in 1 mole of that substance. Okay? Once we convert the mass of the substance that we're looking at, that we're starting with, into moles, then we can convert the moles of that substance into moles of the second substance that we're looking at using that mole ratio that we've been working with. And once we have the mole value for our substance B, we can call it, then we can use our molar mass to figure out how many grams of that substance are present. Okay. So when you're thinking about the steps here, whenever we start out with grams, our first step is going to be to convert it into moles, and we're always going to use the molar mass to do that. In our second step, we're going to take the moles of what we start with, and we're going to convert it into the moles of what we want to end with. And we're always going to do that using our mole to mole ratio from our balanced chemical equation. And then in our third step, we're going to take the mole value for that second substance that we're looking at, and we're going to convert it into mass using our molar mass for that substance. Okay. So here's a question we can look at. Suppose we want to determine the mass in grams of NH3 that can be produced from 32 grams of nitrogen in the following equation. So let's write down the equation and let's write down the information that they give us. They're telling us that we have 32 grams of nitrogen. And they want to know how many grams of NH3 are going to form. All right, so stop sharing so we can write this out. So the first thing that we're going to do is we're going to recognize the two things that they want us to connect, the nitrogen and the ammonia, the NH3, and we're going to write out a mole relationship between them. So we see that every 1 mole of N2 is going to equal 2 moles of NH3. All right. And then we're going to start with the mass value that they gave us. And our first step is always going to be to convert the mass value that we're given into moles. Okay. And to do that, we're going to use our molar mass. So we're going to take our 32 grams of N2. Okay. We're going to look on our periodic table. The molar mass for N2 is going to be the mass of nitrogen, which is 14.01 times 2. So we're going to put the mass value on the bottom, because if we start with grams up top, we want grams on the bottom of our conversion factor. And we put 1 mole in the numerator. With molar mass, you have to remember that the conversion factor from molar mass is always grams in 1 mole. Okay? This 1 mole that I put up here is not affected by this chemical reaction. Okay? The 1 mole is part of the definition of molar mass. Molar mass is going to be grams for 1 mole. The chemical equation numbers, they don't come in until step 2. All right, and that's the only time that we need to apply them. So this first step is just us taking the mass of the nitrogen that we're given and then using the molar mass to turn that into a mole value. So we're going to get 1.14 moles of N2. Okay. Step 2 is going to be to convert the moles of the substance that we start with, which is going to be our N2, into moles of what we want to end with, which is going to be our NH3. Okay, and this is the part. Step 2 is the part where we use our balanced equation. All right, so we're going to take our 1.14 moles of N2, And then we're going to come back up to this equality that we wrote down. And we see that every 1 mole of N2 is going to produce 2 moles of NH3. So we're going to end up with 2.28 moles of NH3. And then our last step, our third step, is going to be to convert the mole value that we find into mass. And for that, we're going to use molar mass again. Okay. The molar mass for NH3, we can count it up here. And the molar mass for our NH3 is going to be 1 nitrogen plus 3 hydrogens, right? So 14.01 plus 3 times 1.008. And we get 17.034 grams per mole. Okay, that's going to be our molar mass for our NH3. So we'll take the moles of NH3 that we just found. And now we're going to set up our conversion factor. Our 1 mole from our molar mass. So remember what molar mass means. It means 17.034 grams in every 1 mole of the substance. So our 1 mole is going to go in the denominator of our conversion factor so that our mole units cancel out. And our mass value is going to go up top. And we end up with 38.84, which we can round to 39 grams of NH3 with our significant figures. Okay, so if you follow through the steps, step 1, we took our mass of our nitrogen and we turned it into moles of nitrogen. Then we took our moles of nitrogen and we turned it into moles of ammonia. Then we took our moles of ammonia and we turned it into a mass of ammonia. All right, let's look at the next part. Next question. And just put it up on the screen so we can see it. All right, so we'll write down our balanced reaction. Always a good place to start. And for this question, they're telling us that we want to produce 45.8 grams of Fe2O3. And they want to know what mass of oxygen is going to be required to do that. Okay. The order that they're giving us the information doesn't really matter. All of these things are connected to each other. So this time they gave us a mass value as a product, and we're going to use that mass value of our product to figure out the mass of our reactant that goes along with it. But we're going to still work through the same set of steps. For this question, they've given us a mass value of the Fe2O3 to start with, right? And that means that our first step is going to be to take the mass of Fe2O3 and turn it into moles of Fe2O3. So to do that, we need to know the molar mass of Fe2O3. So to find the molar mass for our Fe2O3, we're going to do 2 times the mass of our iron plus 3 times the mass of our oxygen. And we're going to add those together. So it's going to be 159.70 grams per mole. Okay, that's our molar mass for our Fe2O3. So in our first step, when we're taking our mass value and we're converting it into moles, we start by doing our 45.8 grams of Fe2O3. That's what we're given to start with. And in our first conversion factor, grams of Fe2O3 are going on the bottom. And our 1 mole of Fe2O3 goes up top. Okay, our second step is going to be to take our moles of Fe2O3 and to turn it into moles of O2. And for this part, we're going to be using our balanced equation. And remember that our balanced equation tells us that for every 3 moles of O2 that we use, we're going to be forming 2 moles of Fe2O3. Okay, that's the relationship that we're going to use in step 2. So if we start out with 0.287 moles of Fe2O3, we're going to put our 2 moles of Fe2O3 on the bottom. And our 3 moles of O2 up top. And we're going to get 0.4305 moles of O2. This is our value from that step. Let me circle the values from each step or box them in. Okay, and now in our third step, we're going to take our moles of O2 and we're going to convert it into grams of O2. And to do that, we're going to use the molar mass of O2, which is 16 times 2, right? So it's going to be 32 grams per mole, which means that we're going to have 32 grams of O2 in every 1 mole of O2. So we're going to take our mole value here. And in our denominator, we're going to put our 1 mole of O2. In our numerator, we're going to put our 32 grams. And we're going to get 13.776 grams, which we're going to limit to 3 significant figures because that's how many significant figures were in our original question. So we'll round this up to 13.8 grams of O2. Okay. Um, and let's look at one more example of this type of question. Screen again. Okay, just a different reaction, but we'll go through these steps again. As a reminder, if you haven't been trying these on your own, definitely work on, pausing the video, trying out the question, and then going back and watching through the solution to see where you were right, where you were wrong, if anything needs to be corrected. That whole process of like trial and error is how you're going to get good at this. So this question tells us that the reaction between the hydrogen and the oxygen is going to produce 13.1 grams of water. And then it asks us how many grams of oxygen are reacted in this process. Okay. But we're going to start in the same places. Okay. We're going to need our molar mass for water, which is going to be 2 hydrogens plus 1 oxygen. So we can write that out as 18.02 grams of water equals 1 mole of water. And then we'll do the same thing for oxygen in our last step. But our first step here is going to be to take our 13.1 grams of H2O, and we're going to put our mass of H2O on the bottom. Our 1 mole of H2O up top. Okay. In our second step, we're going to want to turn H2O into oxygen. So now for our second step, we're going to look at our balanced equation. And our balanced equation tells us that every 1 mole of O2 equals 2 moles of H2O. All right, so for that second step, we're going to start out with our 0.727 moles of H2O. And when we set up our conversion factor, our 2 moles of H2O go on the bottom, and our 1 mole of O2 goes up top. And we're going to get 0.363 moles of O2. Okay. All right, and now we're going to do our third step. And for our third step, we're going to be taking our moles of O2 and turning it into grams. So we're going to need the molar mass for O2. So that's going to be 2 times our 16 which we can rewrite as it's 32 grams per mole, which we would then read as 32 grams of O2 equals 1 mole of O2. All right. So if we have 0.363 moles of O2, every 1 mole of O2 is going to be 32 grams. Sometimes it's easier to like remember where the numbers are supposed to go if you can like talk yourself through it like it's a story. And then we end up with 11.6 grams of O2 as our final value. So we would need to react 11.6 grams of oxygen in order to produce 13.1 grams of H2O. That's what this all tells us. All right, we're gonna skip ahead a couple of sections just to talk about the energy and reactions first. And then we'll backtrack to the other parts of the chapter. But now that we've talked about the setup of chemical reactions and how we can actually do some calculations with them, we can also look at the energy that's involved either in the success of a reaction that's trying to take place. Sometimes a reaction might need a little bit of heat in order for the reaction to actually happen. Or sometimes during the reaction, heat is released. So we're going to look at the reactions and the energy involved either in the start of the reaction or at the end of the reaction, and we're kind of like looking at some of those reactions where heat might be like a product of the process instead. We've already talked about energy, so we are familiar with these two terms, the units of energy, which are going to be joule or kilojoule. Our SI unit for energy is the joule, but when we're looking at the energy that's involved in an entire reaction, either the energy that's lost or the energy that's gained as a result of the reaction, that's usually represented in terms of kilojoules. All right, so we do want to be comfortable converting kilojoules and joules, well, vice versa, either way. But remember this equality to help you set up your conversion factor for it. And what we're going to look at is called the heat of reaction. So the heat of reaction is going to be the amount of heat that's either absorbed at the start of the reaction in order for the reaction to take place, or the heat that's released at the end of the reaction. And the way we're going to calculate the heat of reaction is we're going to look at the heat that the reactants had at the beginning of the process. We're going to look at the heat that the products have at the end of the process, and we're going to subtract these. And that value that we find is going to be delta H. Remember that the triangle is the delta symbol, and that the delta symbol means the change in that particular property. So we're looking for the change in the amount of heat that our products have compared to what our reactants had. Okay. So when you're looking at a chemical reaction in general, what we're going to see is that our reactants are going to interact with each other. And during this process, the bonds are going to break apart. And after the bonds break apart, things are going to kind of shuffle around a bit. And then our products are going to form. And our reactants are going to have a certain amount of heat energy. And our products are going to have a different amount of heat energy. And we're going to compare those two amounts to figure out what our overall heat of reaction is. When we have an exothermic reaction, heat is going to be released as a product. Okay, so what we're going to see in these situations, if you're looking at an actual chemical reaction, you'll notice that heat is going to be put in on your product side of the reaction. Okay. think about it like this. In an exothermic reaction, that the heat is exiting your reaction. Okay. So like I try to look for the similarities in the words to help with the remembering. So like exothermic starts with EX and exit starts with EX. So you could think about it like in an exothermic reaction, the heat is going to be exiting your reaction as a product. Okay. So what you're seeing represented here, they're saying that hydrogen plus chlorine gas produces 2HCl gas and it's releasing 185 kilojoules of heat. Okay. The delta H value for a reaction whose heat is on the product side is always going to have a negative sign. Because remember what we talked about earlier, when heat is lost or when heat is exiting, the sign of that heat is going to be negative because that's going to represent the loss of the heat. Okay. So this reaction is considered an exothermic reaction. Heat is released as a product, and our delta H value is a negative value. All of those things are true for an exothermic reaction. When we have endothermic reactions, in these reactions, heat is going to be absorbed. Okay. When heat is absorbed, we're going to consider it to be a reactant. All right. So when we're looking at a chemical reaction that's endothermic, we would write it out as nitrogen gas plus oxygen gas plus our 180 kilojoules of heat is going to produce two NO gases. Okay. So our heat value is on the reactant side. The way that I remember this is similar to the last one. The word endothermic starts with EN, and the word enter starts with EN as well. So this would be like the entrance, right? The beginning of your reaction, you can consider it like the entrance. The end of your reaction can be the exit. So when heat's entering your reaction at the beginning, it's endothermic. The delta H for endothermic reactions is always going to be a positive number because your reaction is gaining this heat, right? So whenever heat's added, it's going to be positive. Whenever heat is lost, your delta H will be negative. The delta H values that are associated with a chemical reaction can be used as an equality with the mole values that you see in your reaction. So just the way that you have your chemical reaction written out here, let me actually write this out on the board so that we can look at it one at a time instead of all on the screen. When you look at this reaction, sorry, 2H2O liquid produces 2H2 gas plus O2 gas. Okay. We already know how to read that reaction. 2 moles of water produces 2 moles of hydrogen plus 1 mole of oxygen. Sorry, I wrote the reverse. Okay. If we write that the delta H for this reaction is positive 572 kilojoules, what we're saying is that on our reactant side of the reaction, we're going to be absorbing 572 kilojoules of heat. Okay, so we can put our 572 kilojoules at the beginning and treat it just like a reactant. And when we do that, we can create our equalities using our delta H value as well. Okay, so if we have 2 moles of H2O that's going to equal 572 kilojoules of heat. If we have 2 moles of H2, that's going to equal 572 kilojoules of heat. If we have 1 mole of O2, that's going to equal 572 kilojoules of heat. So we can use our delta H value and we can add it to our equivalencies, our equalities that we've been making. Okay. So now let's say that instead of 2 moles of H2O, let's say that I have 4 moles of H2O. Okay. So let's say the question is, if we react 4 moles of H2O, how much heat will be needed? Okay. I know that for every 2 moles of H2O, I'm going to need 572 kilojoules of heat. So if I have 4 moles of H2O, I know every 2 moles is going to require 572 kilojoules. So if I have 4 moles, I'm going to need to have 1,144 kilojoules of heat. Okay, that's how that relationship is going to work. We can take our delta H and we can use it like a conversion factor. All right. Let's take a look at another example. Let me share the screen so we can look at the question. All right, so they give us a balanced reaction here, and they're telling us the delta H value. We see that the delta H value is negative here. And so we know that our heat in this case, it's a negative delta H, so our heat is going to be released as a product. So when they tell us that the delta H value, I'm going to write it down here for a second because we're going to put it into the reaction. When they tell us that the delta H is negative 92.2 kilojoules, what that tells us is that this number, the 92.2 kilojoules, is going to be on the product side. So this negative sign gives us the position of our value. Okay. So when these two things react, we're going to produce 2 moles of NH3 as well as 92.2 kilojoules of heat. Okay. If our delta H value was positive, then that 92.2 would be over here. So now they're telling us, or they're saying how much heat in kilojoules is released when nitrogen and hydrogen react to form 50 grams of the ammonia, the NH3. So we're going to be relating the grams of ammonia to the heat. And so to do that, we're going to want to use the equality that relates those two things. Every 2 moles of NH3 is going to produce 92.2 kilojoules of heat. Okay. Just like with our last set of questions that we were looking at, when we're given a value that's in terms of grams, our first step has to be to take the gram value and turn it into moles. Because when we use our chemical reactions, The comparisons that we're making here are mole comparisons. So when we have a value that's in grams, our first step has to be to take the 50 grams of ammonia and turn it into moles of ammonia. That has to be our first step. Okay. So we're going to use the molar mass of ammonia for this, which we've already calculated in our last slides. It's 17.034 grams per mole. And we're going to take our 50 grams So we're going to end up with 2.935 moles of NH3. And then in our second step, we're going to take our moles of NH3 and we're going to figure out how many kilojoules of heat that we need or that we're going to release. So we have 2.935 moles of NH3, and we see from our equality, every 2 moles of NH3 is going to release 92.2 kilojoules of heat. And we're going to end up with about 135 kilojoules of heat is released in that process. Okay. The other thing that we kind of want to, let's take a look at these next 2 slides. I just want to look at some of the more conceptual links that we can make here. When you're looking at the energy of reactions, you're going to kind of be trying to observe whether your reaction is gaining or losing heat, to also associate it with being an endothermic or an exothermic process. So we can look at 2 different things. We have cold packs and hot packs. Both of these things we can use, if you get an injury, you can either, if you need ice, you can use a cold pack. If you need some kind of warmth, to apply to the area, you can use a hot pack. Inside both of these types of compartments are going to be chemicals that produce a reaction that either absorbs heat or releases heat. And the difference between those reactions is going to be the difference to whether you're feeling coldness come from the pack or heat. So if you need a cold pack, what ends up happening is the ammonium nitrate and the water are going to mix together. And the solution process here, when you have solid ammonium nitrate mixing with water, that's an endothermic process. So it's going to require heat for the mixing to happen. And if the reaction requires heat, that means the reaction is going to be pulling heat into itself from the surroundings. So if you're holding on to the cold pack, you're going to feel it get very cold because the reaction is sucking all the heat into itself. Okay. So this is a representation of an endothermic reaction, kind of in a real life scenario. An exothermic reaction would be the reverse of that. When you have a compartment with something like calcium chloride mixing with water, the calcium chloride and water will mix together. And when those 2 things dissolve, heat is released. And so when you're holding on to that hot pack, you're feeling it warm up because you're feeling the heat being released from this solution process. Okay, that's going to be an example of an exothermic reaction. The last topic for this chapter, and I just wanted to save it for last because it's like, I feel like it's a good culminating topic for the chapter. It's called limiting reactants in a reaction. Okay. And when you're looking at the idea of limiting reactants in a reaction, um, we're talking about the idea that we can take two amounts of reactants and mix them together. And one of those reactants might run out before another one. Okay. Whichever reactant runs out first is going to be our limiting reactant. And whichever reactant we have leftover of, that's going to be our excess reactant. Okay. So a real life example of this, right? Let's say that we have a certain amount of bread, peanut butter bread and peanut butter available to us. Okay. Um, and let's say that for every sandwich that we make, we are going to require 2 pieces of bread and 1 tablespoon of peanut butter. If I have 20 slices of bread available, but I only have 1 tablespoon of peanut butter available, I can only make one sandwich. Even though I have 20 slices of bread, I can only make one peanut butter sandwich because I don't have enough peanut butter to make any more than that. So in this first example, our limiting reactant is going to be the peanut butter, and our excess reactant would be the bread. Let's say that I only have 4 slices of bread, but I have a full jar of peanut butter. A full jar has many tablespoons. If I only have 4 slices of bread, I can still only make 2 sandwiches because after I make 2 sandwiches, I don't have enough bread to make anymore. So my bread becomes my limiting reactant in that case. And my peanut butter is going to be my excess reactant. Okay. This is the idea of limiting reactants. And this is what we're going to talk about in this section. So a limiting reactant in a chemical reaction is going to be the substance that gets used up first. And it's going to limit the amount of product that can form because after our limiting reactant is used up, our reaction has to stop because one of the pieces is missing. And the reactant that does not completely get used up is going to be called our excess reactant. Okay. So you are going to know that you are looking at a reaction where a limiting reactant might be a possibility when the problem gives you 2 reactant values to work with. Okay. If you have 2 reactant values that you're given information about, you have to decide which of those reactant values is going to run out first. Okay. In any reaction, when they're only telling you information about 1 reactant value, then you can assume that that's the reactant value that you're going to focus on and that you're going to use to figure out the amount of product. But when you're given 2 reactant values, you have to look at both of those reactants. You have to see how much product each one of them could potentially produce when it's completely used up, and then use that information to figure out the limiting reactant. Okay. So this is an example. We're going to look at this step by step. We're going to start out with our balanced equation. Notice in this question how they're giving us information about 2 of our reactants. They're giving us information about the CO and about the H2. And they're asking us how many moles of our product can form from that. So if we have information about both of these reactants, then we have to figure out which of these reactants is going to run out first. Okay. Um, any limiting reactant question involves the same two steps to start with. Okay. I like to set up my reaction like my with the other stoichiometry questions we looked at. And I like to write the numbers of each of my reactants underneath their their position in my balanced equation. And our question here is going to be how many moles of the methanol are going to form. Your first step here is always going to be a two-part process. You have to figure out, we'll say step 1A, find the moles of CH3OH from your CO2 amount from your first reactant. And then step 1B is going to be to find the moles of your CH3OH from your second reactant. In any limiting reactant question, this is always your first set of steps. Find the amount of product that each reactant can produce. Okay? We're going to do this by using our balanced equation coefficients. So if I have 3 moles of CO2, I can look at my balanced equation. I know that when there's no number out in front, it just means that there's a 1. And I know that for every 1 mole of CO2 that I use up, I'm going to form 1 mole of CH3OH. So if I have 3 moles of CO2, I'm going to form 3 moles of CH3OH. If I was able to use all of my CO2 up, I'd be able to form 3 moles of CH3OH. Okay, now I'm going to do the same thing for the H2. I'm starting out with 5 moles of H2. Every 2 moles of H2 that I use up is going to form 1 mole of CH3OH. Okay, that means that if I use up all 5 moles of my H2, I'm going to be able to produce 2.5 moles of CH3OH. Okay, at this point, you're going to compare these numbers that you have. The bigger number it's a number that can't happen. Okay, the bigger number can't happen because after we form 2.5 moles of CH3OH, we're going to run out of H2. So there is not enough hydrogen to make 3 moles of CH3OH. There's enough carbon dioxide to make it, but there's not enough hydrogen to make it. Okay, so we're going to use the smaller value, use the smaller product value to find the limiting reactant. Okay. And the smaller product value has its own special name. It's called the theoretical yield. Okay, so like highlight that, put a star around it, circle it, whatever. But the smaller product amount is called the theoretical yield. So this number here, the smaller number that we found, the 2.50 moles of CH3OH, that's our theoretical yield. And the reactant that made the theoretical yields. So if we go back to the beginning, the H2 is the reactant that made our theoretical yield. The reactant that makes the theoretical yield is the limiting reactant. Okay. So here, our limiting reactant in this question, our limiting reactant is going to be the hydrogen gas. And the amount of product that we're forming, which we can also call our theoretical yield, is going to be 2.50 moles of our CH3OH, our methanol. Okay. If you're given a limiting reactant problem with mass values instead of mole values, then we're going to apply the same steps that we've used previously. And first, we'll take those grams and turn them into moles. And then we'll take the moles of our reactant and we'll turn them into moles of product. Okay. Let me just put the steps up on here before we go to the next example. So if our quantities of reactants are given in grams, then our steps would be to convert the grams of each reactant into moles first, and then use our mole to mole conversion factors to convert the moles of reactant to moles of product. Okay. And step 3, we can apply to our theoretical yields only. Like you don't need to find the gram values for both reactants. If you have already figured out which reactant is your limiting reactant, then you can use that calculation and apply step 3 to it. Okay. And remember that our reactant that produces the least amount of product is going to be our limiting reactant. So we're going to look at this example next. They're asking us how many grams of CO are formed from 70 grams of SiO2 and 50 grams of carbon. And notice in this question, nowhere in this question do they use the words limiting reactant or theoretical yields. They're expecting you to understand that when you're given mass values for 2 of your reactants, that the question is automatically going to be a limiting reactant type of question. Okay, so as soon as you see mass values or mole values for 2 of your reactants, you automatically have to apply the limiting reactant and theoretical yields steps. Okay. So we have our react. So one change that we're going to make to the reaction that we saw on the last slide, before we do this problem out, they wrote us like a truncated version of this equation. Okay, because they wrote out SiO2 plus 3 carbons gives us 2 COs, which is true, but they left out the other part of the reaction, which is that it also produces silicon carbide as a product. I think that they were intending to do that to make it less confusing. But it also, we've gone through balancing the reactions now. So we would be able to tell that if you have silicon, oxygen, and carbon on your reactant side, you need to have silicon, oxygen, and carbon on your product side as well. Um, what this question specifically asks for, though, right? It says we've got 70 grams of the SiO2 and we've got 50 grams of the carbon, and it's specifically asking us how many grams of the CO2 are going to form from, or sorry, of the CO are going to form from that. So even though there's more than one product listed, they're telling us the product that we focus on. Okay. So you just use the product in the question that they're asking you about. And we're going to start this the same way that we started the last limiting reactant question, where we take each reactant. So we have our 70 grams of SiO2. And the first thing that we're going to do is to figure out how many moles of our product that it will form. Okay. And then in our second step, we'll call it step 1B, we'll take our 50 grams of carbon and we're going to figure out how many moles of CO that will form. Okay. And we're just going to focus on the reactants and the product that are mentioned in our question. Okay. But we're going to know that for this part, if they're giving us a mass value to start with, the first thing that we have to do is use the molar mass of the SiO2 to convert the grams of SiO2 into moles of SiO2. So that's going to be 28.09 plus 2 times the mass of oxygen. So we're going to have 60.09 grams of SiO2 in every 1 mole of SiO2. All right, and so now we can take our 70 grams and the first thing that we'll do is use the molar mass to convert it into moles. And now we want to convert it into moles of carbon monoxide. So we look at our balanced equation. Every 1 mole of SiO2 makes 2 moles of carbon monoxide. So we're going to put our mole of SiO2 on the bottom so that our units cancel out. And we're going to put our 2 moles of carbon monoxide up top. Okay, so if we use up all of our silicon dioxide, we can make 2.33 moles of carbon monoxide. All right, that's our first step. Now we're going to do the same thing for the carbon, and we're going to see how much carbon monoxide we can make from that. So we have 50 grams of carbon to start with. We know from our periodic table that there's going to be 12.01 grams of carbon in every 1 mole of carbon. So if we have 50 grams of carbon, that's going to leave us with 4.163 moles of carbon. And now we're going to look back at our balanced equation. Every 3 moles of carbon produces 2 moles of carbon monoxide. So our moles of carbon by itself go on the bottom so that our units match. And our moles of carbon monoxide go up top. And we see that if we use up all 50 grams of our carbon, we're going to end up forming 2.78 moles of carbon monoxide. Okay. Once you get to this step, Now you have to start to interpret this. And remember, whatever the bigger number is, this number is no good to you. The bigger number can't happen because we're going to run out of SiO2 before we can make 2.78 moles of carbon monoxide. So this tells us that our limiting reactant is going to be SiO2. And it tells us that our theoretical yield is going to be 2.33 moles of carbon monoxide. Now, a theoretical yield value is a number that represents the amount of product that you form. Your theoretical yield value can be in the units of moles or grams or kilograms, whatever amount value that you'd like. So you're going to use the question itself to figure out how you present your final answer. Okay, in this question, they asked us specifically how many grams of carbon monoxide are formed. So we have the theoretical yield here represented in moles. And so what we're going to do is we're going to use the molar mass of carbon monoxide. If we want to do a little molar mass calculation down here, we can. Carbon is 12.01 grams per mole. Oxygen is 16. So if we add those together, we're going to have a molar mass of 28.01 grams per mole. Okay. So if I have 2.33 moles of carbon monoxide, I know that every 1 mole of CO is going to be 28.01 grams of CO. Which is going to leave me with 65.3 grams of CO formed when this reaction is finished. Okay. Let's look at one more example, and then we'll just mention one more thing. Share my screen again. Here we go. Take a look at that question. In the following reaction, they give us the ammonia reaction again. Calculate the amount of NH3 that can be formed when 2.50 grams of nitrogen gas reacts with 2 grams of hydrogen gas. So again, in this question, nowhere in this question specifically did they mention the words limiting reactant or theoretical yields. But they gave us 2 mass amounts for our reactants, 2 amounts of our reactants. They could be masses or moles. But when you're given 2 reactant amounts in the question that you're presented with, they're telling you that it's a limiting reactant problem without using the specific words. Because they're saying like you're starting with 2.50 grams of the ammonia, you're starting with 2 grams of the hydrogen, and you have to see which one of those is going to run out first, and then how much product you're going to end up with. Okay. So we're going to start with our same set of steps. For 1A, we're going to take our 2.50 grams of nitrogen. And our first step, we're going to use the molar mass of nitrogen to turn the grams of nitrogen into moles of nitrogen. So the molar mass for nitrogen is 28.02 grams in 1 mole. And then we're going to use our balanced equation, which tells us that every 1 mole of nitrogen, right? There's an assumed one in front here. Every 1 mole of nitrogen produces 2 moles of NH3. So if I use up all of my nitrogen, I can make 0.178 moles of NH3. Now I'm going to do the same thing for my hydrogen. I'm starting out with 2 grams of hydrogen. The molar mass for my hydrogen is going to be 1.008 times 2. So it's going to be 2.016 grams of hydrogen in every 1 mole. And then from my balanced equation, I see that 3 moles of hydrogen get used up for every 2 moles of ammonia that form. Okay, so I look at these two numbers. I take that bigger number, and I would really recommend when you're working out the problems to physically cross out the bigger number for yourself so that you don't accidentally use it, especially when you're taking multiple choice questions. Sometimes there's the reaction of seeing a number on your paper that you're working or in your calculator, like seeing a number that matches a number that's an answer choice. But a lot of the answer choices that they're going to be giving you are answer choices from like the wrong steps that you're taking. Okay, so if they put 0.661 moles as an answer choice, that would be they were doing it on purpose to try to be tricky. So if you physically on your paper, you physically mark that off and say, no, I'm not using that, then even if you see it as an answer choice, you won't feel like you need to pick that one. Okay. So from this information that we're seeing, we know that this value is going to be our theoretical yield in moles. And when we trace it back, the reactant that made our theoretical yield is the nitrogen. So our limiting reactant is going to be our nitrogen, and our theoretical yield, which is the amount of product that we're able to form before one of our reactants runs out, is going to be 0.178 moles of NH3. And then we can take this value and we can convert it into whatever unit our answer choices are in. So if our answer choices are in moles, then we're already done. But if our answer choices are in grams, then we're going to use the molar mass for ammonia, which we've calculated previously. And we'll end up forming 3.03 grams of ammonia from that. Okay. Um, the last thing that we want to talk about for this section and this chapter is related to our theoretical yields. But it's going to be more in relation to how actual reactions work. Okay. There are calculations that we can do on paper, and then there are the way that actual reactions happen in lab space. Okay. When you're doing a reaction in lab, you're going to see that a lot of times your reaction might not go fully to completion. Or maybe when you're doing some measurements, some of your reactant or some of your product gets lost. Or maybe you just take a mass measurement wrong. Okay. There's a lot of things that can happen where that leave you with a product amount that you measure at the end that isn't as much, it's not as high as you would expect it to be. Okay. These theoretical yield values that we're calculating, this is the maximum amount of product that we should be able to form if we use up all of our limiting reactant. Okay. But our theoretical yield values are like these perfect numbers. They're the perfect values that should be produced if our reaction goes perfectly. Okay. This term here, actual yield, this is our reality. This is the amount of product that is actually obtained at the end of the experiment in a lab when you're working. This is the real number that you get. Okay. And we're going to compare these two values. And the comparison of these two values is called our percent yield. So our percent yield, it's like a measurement of how efficient our reaction was, how efficient our process in lab was. To calculate our percent yield, we're going to take the actual yield value, which is the number that you'll end up with at the end of your experiment. And we're going to divide it by the theoretical yield value, which is a number that you will calculate before you do the experiment. Okay, actual yield divided by theoretical yield times 100, that gives us our percent yield. So this is an example of what a percent yield type of question would look like. Here they're saying that on a space shuttle, lithium hydroxide is used to absorb exhaled carbon dioxide from breathing air to form lithium hydrogen carbonate. What is the percent yield of the reaction if 50 grams of the lithium hydroxide produced or gives 72.8 grams of lithium hydrogen carbonate? So in this question, we have to decipher the information that they're giving us here. We have our reaction. Okay. And when we've looked at the theoretical yield calculations from our limiting reactant questions, right? You know, when we're labeling what we have available here, right? We put our amount of reactant on one side and we put a question mark by our product side. And when we're solving for this product amount, this number that we solve for, this is the theoretical yield. Okay. When we use our reactant amount to find a product amount, that's our theoretical yield. What they also gave us in this question was they gave us a number. They said, this is how much lithium hydrogen carbonate that you ended up with. When they tell you a product amount, that amount is our actual yield. Okay. The actual yield is when the question specifically tells you how much product is formed. Okay. And so what we're going to do, we want to find the percent yield. That's the question they asked us. They said, find the percent yield. Well, to find the percent yield, we'll write the formula for it over here. The percent yield is going to be the actual yield over the theoretical yield times 100. They gave us this number. We have to find this number, and then we can calculate the percent yield. All right. To find your theoretical yield, if you only have one reactant, then it's only one step, right? We don't have to worry about finding a number for the CO2 because they're just telling us that there's a lot of CO2 present. There's way more CO2 than lithium hydroxide. So they're saying that if they give us one reactant value, we can just find the theoretical yield from that one reactant value. So we're going to take our 50 grams of LiOH, and we're going to use the molar mass of the lithium hydroxide. Let's do our little molar mass calculation up here. So lithium is 6.941. Oxygen is 16. And hydrogen's 1.008. So we'll add all those together. So that's going to be 23.95 grams per mole. Okay, so if I have 50 grams of lithium hydroxide, every 23.95 grams is going to be 1 mole. Okay, and if I have 2.09 moles of lithium hydroxide, I can look at my balanced equation. Every 1 mole of lithium hydroxide makes 1 mole of lithium hydrogen carbonate. So it's a 1-to-1 ratio here. So if I have 2.09 moles of lithium hydroxide, I will end up with 2.09 moles of lithium hydrogen carbonate. And now I can take that value and I can figure out the mass of that. This is going to be my theoretical yield in moles. But I'm going to want a theoretical yield in grams because they gave me my actual yield value in terms of grams. Okay. So I'm going to need a molar mass value for the lithium hydrogen carbonate. So let's do a molar mass calculation up here. 6.941 plus 1.008 plus 12.01 plus 3 times 16. All right, so we get 67.96 grams per mole for our lithium hydrogen carbonate. Okay, so we're going to take our mole value here, and we'll say, all right, if I have 2.09 moles of LiHCO3, I know from the molar mass that every 1 mole is going to be 67.96 grams. So I should be able to form 142 grams of my lithium hydrogen carbonate. So this is going to be my theoretical yield in grams. Okay, so now I have my theoretical yield and I have my actual yield. So now I'm going to find my percent yield. So my percent yield is going to be 72.8 grams, which is my actual yield, divided by 142 grams, which is my theoretical, times 100. And that's going to give me a percent yields of about 51.3% for that reaction. Okay. And that's the last part of chapter 7.